So looking at problem 9 now, a cylindrical block of outer radius r and height h with density rho is supported by a vertical massless spring with spring constant k and is half dipped in water in equilibrium. So we have to note that there is this spring which has a spring constant k and it is half dipped in water. So right, and we're given its radius, height and density. So we have to find the time period of small oscillations. Again, this is a slightly familiar setup and people have usually, dealt with it by the time they sit for entrance examinations. So we think you should do it right now. So let's go through.
So we have already dealt with this kind of problem in the starting, but there was no fluid in the container. There was only spring block system.
Right.
Then I have said that it oscillates about the equilibrium position.
Correct.
There we have considered the force from the initial force which the spring gives from the natural length.
Okay.
But that is not necessary.
Right.
Because that is cancelled by the mg.
Okay.
Similarly here also this can be, when you use force method, this can be solved by two ways.
Right.
By considering forces from the natural length itself or by considering forces from the equilibrium.
Right.
Both will land up to the same solution, but if you do it from equilibrium, it is very simple.
Right.
So let's use force balancing method at the equilibrium position.
Right.
So let's draw the FBD of this block.
Okay.
This is the block and the weight is acting downwards, which is mg. But this weight is already counted upon by the equilibrium extension,
right,
which is k delta xa.
Okay.
After this, the extra forces which are acting on it are, I'll write it as k capital X, capital X, which is the extension after the equilibrium.
Okay, so we are talking of capital X as the extension after equilibrium.
Yeah.
In the sense that, can you show in the figure what exactly capital X is?
Suppose this is the equilibrium position.
Right.
Now, if the block goes inside by X.
Okay.
From the equilibrium.
Right.
That is what I mean by capital X.
Okay.
So spring extends by capital X from the equilibrium position.
Right.
If we take those, we'll land up at the solution, because in the equilibrium the weight is counted upon by some extension from the spring and the buoyant force.
Correct.
So Kx is acting upwards and then there is this Fb.
Okay.
And then we have Ma.
Right.
So what the equation turns out to be, F is equal to minus Kx minus rho Vg.
Okay.
Let's say this as capital X.
Yep.
Because we are taking from the equilibrium.
Right.
So V is nothing but the extra volume which is being immersed.
So we can write that in terms of X.
Exactly, in terms of capital X.
Okay.
Is minus Kx minus pi r square into capital X into rho water G.
That is because we are given it's a cylindrical.
Yeah.
Okay.
This
so
is
obviously we can take X outside the brackets and the rest of the term will become omega square.
Exactly. So minus K plus pi r square rho water G into X. So again we can see that F is proportional to X and this is the proportionality constant, which is again m omega square.
Right.
So
from here we can find out omega and T and whatever. So what the expressions for T will be?
So
omega.
m omega square is K plus pi r square rho water G.
Right.
So we get omega as under root K plus pi r square rho water into G by M.
Okay.
So time period is nothing but again 2 pi by omega.
Right. So you saw this was problem 9 and we had a
and this is a very important trick which has to be used, because if forces are calculated from the initial thing, like if you include these forces also, the problems get messier, because anyway these are going to get cancelled. If you write them also, they are going to get cancelled because they have arrived to that position because of equilibrium.
Okay.
So if you write them also, they are going to get cancelled. So
Can you actually summarize what this technique is? And I think it will be very useful for our students. So can you again summarize what we don't have to do here?
Yeah. So when you in the question it said that the block is in equilibrium in half dip position.
Okay.
So when it is in equilibrium, the spring is stretched by delta x.
Okay.
And there is some delta FB also.
Right.
So this mg is countered by this delta FB and this k delta x.
Right.
So when you
if we decide to write those forces, we don't actually have to because they are equal.
They get cancelled anyway.
Okay.
So when you disturb this block from equilibrium by capital X,
right,
and then write the forces including these,
okay,
then it gets messier because anyway these are going to get cancelled.
Okay. In fact, and there might be a room for an extra variable mistake,
exactly,
and you might take the wrong terms common, and eventually your time period omega will come out to be wrong.
Yeah.
So it's always okay to exclude forces which are already equal and cancel out each other because anyway they will not be playing any role.
Exactly.
Okay. So you saw this very significant trick, and will also reduce your work actually. When you're sitting in entrance examinations, you don't want to write big equations involving 7-8 terms. So this will make your work faster, and you just saw how the sync block system can be shown to follow SHM and under these conditions. And from there, we wrote the simple force equation for the system, excluding these forces which anyway cancel out each other. So this is a simple trick which you can follow to solve problems faster. So this was problem 9, and we'll look at the next one now.
Alright, so here we have question number 10, which says a simple pendulum of mass m is suspended by a massless string of length L. The mass also carries a negative charge Q. The pendulum is placed in a uniform electric field of strength E, directed A vertically up, B horizontal. Find the time period in each case. तो ये सवाल में कह रहा है कि एक पेंडुलम है जिसका बॉब जो है वो मास m का है और उसे हमने सस्पेंड कर दिया एक मासलेस स्ट्रिंग से जिसकी लेंथ l है. मास में एक नेगेटिव चार्ज q भी है और उसको हमने एक यूनिफॉर्म इलेक्ट्रिक फील्ड E की स्ट्रेंथ जिसकी है उसमें डाल दिया. तो जब वो इलेक्ट्रिक फील्ड वर्टिकली अपवर्ड्स होगी या हॉरिजॉन्टल होगी तो उन दोनों केस में टाइम पीरियड क्या होगा, ये सवाल है. हाउ शुड वी अप्रोच इन दिस पर्टिकुलर क्वेश्चन?
फर्स्ट लेट्स सॉल्व इट बाय एनालिटिकल वे बाय यूजिंग द फोर्स मेथड. Then we'll look into a shortcut which can solve these kind of problems. So let's draw the FBD first.
Okay.
This is the equilibrium position.
Yeah.
And this is the bob.
Okay.
And it is displaced by an angle theta. So when we draw the FBD, the tension is acting this way at an angle theta, and there is force QE vertically downwards, and it should be carefully noted that E is up, so and Q is negative, so the force on it will be in the downward direction,
right,
and mg will also be in the downward direction,
right.
So let the point of oscillation be O.
So I have a question here. Can't we directly now take the mass of the bob as mg plus QE by G?
Yeah, we can actually. That is a shortcut. We take effective gravity.
Yeah.
Instead of effective mass, we take effective gravity. We divide the force on it by the mass, so we get the effective gravity. That shortcut let's discuss after the force method.
Yeah, because Q is always going to be constant, and mg is also going to be constant, so it can effectively
both
look
can
like
be clubbed together.
Yeah. Okay. But anyway, so you're going with the long method so that we have
let's
analysis
do it by
clear.
the method and then go for the shortcut.
Sure. Yeah.
So the torque about O is minus mgl sin theta minus qel sin theta.
Okay, so let me understand, how did you get that? So mgl sin theta. So mg is this way. And
L is this way, and
okay,
because it is inward, the cross product is into the plane.
Sure.
The minus sign appears.
Yeah.
So we use the approximation sin theta is approximately equal to theta. Very famous approximation. Very used.
So when theta is very small, we take sin theta.
When theta is small.
Yeah.
And it is in radians.
Yeah.
So what do we get now? Minus mgl minus ql into theta.
Yeah.
What we can observe is that restoring torque acting on the particle is directly proportional to the angular displacement. This means that the body is in SHM.
Okay.
So, and this is the K. So what we can do is m omega square is equal to mgl plus ql. So we get omega as under root g plus qe by m into l.
Yeah.
So this is the omega. So let's solve the same problem by utilizing our shortcut. So let's see how that shortcut
time
works.
period, we have to take out the time period, right?
Yeah, time period is nothing but 2 pi by omega.
Yeah. So that'll be our time period. Okay.
So let's look into our shortcut. So there is this, consider this in equilibrium position. There is this tension acting and mg and even qe both in the downward direction.
Okay.
So this shortcut has come from, just observe the formula for simple pendulum. Formula for simple pendulum is 2 pi under root L by G.
Yeah.
Since Q is something like mg, which is acting downwards, we can find out an effective G. The extra amount of G which is being contributed by QE.
Sure.
And then add that to the already available G.
Absolutely.
So so what we can do, we can rewrite the formula as T is equal to 2 pi under root L by G effective.
Yeah, right.
And G effective can be written as F net by M.
Yeah.
So if we use this shortcut here, F net is nothing but QE plus mg divided by M. This is G effective.
Okay.
So we get the same thing again.
Yeah. Okay. I have a question.
Yeah.
So you taking G effective. Why aren't you taking M effective? So even the M effective could. Yeah.
Because in the time period we don't have the M term only.
Yeah.
In the time period we don't have the M term. So if we take M effective, that doesn't actually affect the time period.
Exactly.
Instead, let's take the G effective.
Right. So time period will not change even if the mass changes, but in this case, since the force is changing and so the time period is changing, which means acceleration, effective acceleration due to gravity must be changing, and hence we would take G effective and not M effective. Alright. So we got the G effective here, putting it in 2 pi root L by G, we would get the time period. Okay.
And yes, this method can be extended to many other problems also. For example, you have this problem of pendulum in a lift.
Yeah.
When the lift is moving up with an acceleration A or moving down with an acceleration A, so then the G effective will be G plus A or G minus A, and the time period formula can be easily found out by just substituting the G effective and getting it instead of using the force method or energy method.
Right.
And similarly, the B bit also we can solve it by this shortcut. In B bit, the electric field is horizontal. So when we draw the FBD, so the force QE is on to right.
Yeah.
And mg is downwards.
Right.
So the net forces, since they are perpendicular and they are vectors, F net is under root mg square plus qe square. So you got F net divided by M will give you G effective, and substitute that in 2 pi under root L by G effective, you get the time period.
But my question is, see, QE is in horizontal direction, whereas mg is in vertical direction, which means QE will not have any component in the line of mg, right?
It may not have,
It will not have. So F net in vertical direction is still going to be mg.
Yeah, but the thing is, it is not oscillating about the vertical. It is oscillating about an angle theta. So both of them combinedly have produced a field, have produced an equilibrium position about an angle theta, and now this oscillates about this angle theta.
So you're saying a mean around which it's oscillating is itself in an angle theta.
Exactly.
Right.
And that is affected because of QE. And that is affected because of QE.
Yeah, right. So how do we solve this? So let's take the components and not take out the F net just like that. Let's take out the components and see what will happen.
And the equilibrium position theta can be found out by using vector calculus. That is, tan theta is equal to QE by mg, because there is this point like this and QE is acting this way and mg is acting this way. So from, say, this as f1 and this as f2, this is what we have learned in our first chapter, vector calculus, that theta is equal to tan inverse QE by mg. So this pendulum will oscillate about this line, which is inclined at an angle theta, and the value of theta is given by this expression.
Okay.
So, and the frequency or time period of oscillation, that can be calculated by the shortcut, which is f net. I'll write that more clearly here.
Yeah.
F net is equal to mg whole square plus QE whole square under root.
So,
because these two forces are perpendicular to each other.
Right.
So mg whole square plus QE whole square under root.
So F net is the net force applied in the direction, this direction, which is in angle theta to the perpendicular, which is actually the direction of the mean.
Mean, yeah.
Right? Okay.
So F net is acting in this direction.
Yeah.
Which is at an angle theta.
Right. Yeah.
So now we get G effective.
Right.
As F net by M. So when we substitute F net into it, we get G effective as G square plus QE by M whole square under root.
Right.
So time period is nothing but 2 pi under root L by
G effective. Alright. Right, so this was a shortcut way to solve find the time period of a
particular pendulum.
Yeah, so of a particular pendulum, wherein there might be other forces applied on the particular bob, and those forces could be in terms of electric field, it could be in terms of any other gravitational field,
magnetic field, maybe.
Yeah, something which is not changing, something which is constant, and then accordingly you can find out the G effective and then put it in the formula 2 pi root L by G, instead of applying another equation and trying to find out the time period right from scratch. Alright, so that was question number 10. Alright, so here we have a different kind of question, which is different from the kind of questions we've been solving before, wherein we had equations related time period finding and everything else, but in this case we have something related to a graph. So looking at the graph, we have to find whether the time period or acceleration or everything else here is correct. Alright, so let me read out question number 11 to you, which says the figure shows a graph velocity versus displacement from mean position of a particle in SHN. So this is the figure which shows us the velocity versus displacement graph, and we have to tell whether one of these statements is correct or more of these statements is correct. So the first statement is the time period of the particle is 1.57 seconds. So tell me how we're going to approach about it.
Yeah. So let's look into the intercepts first. Okay, what does this intercept tell us? It is the maximum of velocity.
Yeah.
So Vmax is always A times omega.
Yeah.
And what does the x-intercept say? That gives the maximum of x. Amplitude. That is the amplitude.
Yeah.
So x max is the amplitude.
Right.
So when you divide Vmax by Amax,
Yeah.
you get the omega.
Yeah.
So omega is equal to y-intercept
10 by
by
2.5.
x-intercept.
Yeah.
So we get 10 by 2.5, which is
4.
4.
Right.
So
4
from
is
this
omega.
we can find out the time period.
Mhm.
So time period is nothing but 2 pi by omega. So 2 pi by 4, which is pi by 2, approximately equal to 1.57 seconds.
Interesting. So the first statement is correct, wherein it says the time period of the particle is 1.57 seconds. Okay, this is correct. B is the maximum acceleration is 40 centimeter per second square. How do we do that?
Yeah.
So I think in this case, acceleration would mean dv by dx, right?
Yeah, like there is another simpler
dv
method
by
also.
dt would be the acceleration.
dv by dt would be the acceleration, but there is another simpler method also. Acceleration, like the question asks for maximum acceleration. So acceleration maximum is nothing but minus a omega square.
How do we get that?
That comes from x is equal to a sine omega t plus phi. So a is equal to d square x by dt square.
Yeah.
So you get it as, so when you differentiate it twice, you get omega square out. So a omega square, and sine becomes cos, and again cos becomes sine.
Right.
So sine omega t plus phi. And the maximum of sine omega t plus phi is 1.
Right.
Or minus 1. So a max will be a omega square then. So that is how we arrive at this simple result.
Right.
So by looking at the graph, some people might go into a different way, but looking into the basics will get us through.
Yeah.
So again, a we got as 2.5 into omega square is 16. So that will lead to 40
Okay.
meters per second.
What happened to the minus sign?
Oh, like this is minus, right? So a max is, it can be plus or minus. Minus says it is in the other direction. Minus says it is in the other direction, plus it is in the opposite direction. So the magnitude. So 40.
That is also correct. Okay. Part number C is.
Yeah.
Yeah.
Part number C says.
Part number C says the velocity of a particle is 2 root 21 centimeter per second when it is at a distance of 1 centimeter from the mean position.
Yeah. So it asks us to find out velocity when the particle position is given. So we need to find out a relation between the particle position and the velocity that we can get from the given graph. The given graph is an ellipse.
Yeah.
So we can write the ellipse equation as follows. That is x square by x-intercept square, which is 2.5 square, plus y square, which is v square, by y-intercept square, which is 10 square, is equal to 1. So we get v square is equal to 10 square into 1 minus x square by 2.5 square. So we get v as 4 times under root 2.5 square minus x square. So by plugging in the value of x is equal to 1, we can arrive at the velocity.
Right.
So when we put v for x is equal to 1, we get it as 4 under root 2.5 square minus 1, which is equal to 2 root 21.
And how do we get that?
Yeah. So 2.5 square is nothing but 6.25. So 4 under root 5.25.
Yeah.
So when you approximate it, you get it as 2 root 21. Take a 2 inside and then you get it.
Alright. Okay. Alright. So it's coming out to be correct. C part is also correct, and and none of the above is not correct.
Yeah.
So alright, so here we learned on how to solve questions based on graphs. So that was question number 11.